Okay, so this time my wonderful picture is not going to go to waste. So this is a square pyramid. It's got the square base 2, 3, 4, 5. I guess apex is the word for that. Is 1. And then what I drew here is the poset of faces. Yeah. So you have the empty face. Every polytope has the empty face. Then the vertices 1, 2, 3, 4, and 5. All the different edges. All the different faces. And I'm labeling by the vertex set. So 2, 3, 4, 5 is the base, for example. And then I have the full polytope. And so I order them by inclusion. Okay. So if this is my polytope P, then this is what's called the face poset or the face lattice LP. Okay. And so what I want to begin with today. So I want to do. My plan is to do 2 things. We'll see how the time goes. But first, I want to remind you about the topological interpretation of Mobius numbers that we had last time, and use that to understand this poset a little bit better and compute its Mobius function. And then we'll see if there is time. Then I actually wanted to teach you a little bit of matroid theory and show you how it's related to this stuff. Okay. But maybe I should begin by reminding you of our topological point of view. So remember that we had P. P was a poset with a 0 and a 1, and P bar was the poset with the 0 and the 1 removed. And then we define the order complex delta of P bar. This was a simplicial complex where the vertices are the elements of P bar and the faces are the chains of P bar. Okay. I might have said simplices instead of faces, but in the context of simplicial complex, it's the same thing: faces and simplices. And so the main theorem that we proved last time, beautiful theorem, is that the Mobius number of my poset P is equal to the reduced Euler characteristic of the order complex of P bar. Okay. And this is a very useful result, and one thing that it does is that it tells us that these Mobius numbers, we have already interpreted them combinatorially. We have interpreted them algebraically in terms of Hopf algebras, but they also can and should be thought of as a topological quantity. Okay. So this is what we proved last time, and I want to talk about an application of this. Which is phase lattices of polytopes. So P is going to be a polytope. I guess it's a little bit unfortunate that poset and polytope both start with P, and so I'm calling both of these things P. But P is a polytope, and LP is going to be the poset of faces of P ordered by containment. Okay. And so that's what I drew in my picture over there. And whenever I call a poset L, you should immediately suspect that it's probably a lattice. Okay, and so my next claim is that this is a lattice. So LP is a lattice. Meaning that I have a join and a meet operation. Now, remember, whenever you have a finite poset, if you want to prove that it's a lattice, you just have to either do the join or do the meet. And when you have one, as long as you have a bottom and a top element, which this one does, then you know it's a lattice. So which one would you prefer to tell me? What is the meet or what is the join of two faces? So given two faces of this polytope, you should either tell me what the meet of them is or what the join of them is. So that's kind of the easiest thing to try, is that you could take, for two faces, their meet will be the intersection. And the question is, if you intersect two faces of a polytope, do you get a face? Well, the answer is yes. The answer, at least in 3 dimensions, this is very clear. If you intersect two faces, you're going to get a face. If you want to know this in higher dimensions, you have to, I guess I haven't technically defined what a polytope is, and so you would do that, but then by the definition it's very clear that the intersection of faces is a face. Okay? And I should say, I'm going to be talking about polytopes today, and if you don't know too much about polytopes, then I think from the 3-dimensional picture you will see the main features, and you can prove all of the things that I'm going to say in higher dimensions. And if you know a little bit more about polytopes, you can think about how to prove them. But yeah, so LP is a lattice where the join of two faces is going to be the intersection. Okay, and the meet is also, you can just say it's the smallest phase that contains them both, but that's a little bit trickier to know that there's a unique minimal phase that contains them both, but it can also be done. Okay, this is a lattice, and the proposition that I would like to show is the following. The Mobius number of this poset is going to be nice. It's just going to equal -1 to the dimension of the polytope. Okay, and you could do it in this example. You can compute the Mobius numbers, and you'll see that they go 1, -1, 1, -1, 1. Okay. So let's go ahead and prove this. And this is going to be one of these proofs by example. I'm going to indicate to you how, in this example, why this result is true. And I'm going to claim that holds in general.
Is it 2, 3, 4, 5? Wouldn't its Mobius number be?
You're worried that the number is not what it should be?
Yeah. Because
if I drew this correctly, and if you did this carefully, then it is what it needs to be. So here you have 1,
right.
-1's here, 1's here, and so this is a -1. Yeah.
And that grade of the poset is all the two-dimensional bases.
Right. Maybe that's another thing worth mentioning, that this is not just a lattice, but it's a graded lattice, where the floors are given by dimension, right? So these are the 0-dimensional faces, the one-dimensional faces, the two-dimensional faces, and so on. Yep. I said this was the. I think I said it was the join, and I meant the meet. Yeah. I've never liked these names. I've always confused. I mean, I work on this. I've worked on this for many years, and I still get join and meet mixed up. But meet is below, and join is above. Proof by example. So what I'm going to do is the following. I'm going to say, okay, well, you want me to compute the Mobius function of this poset. Well, what I'm going to do is compute this Euler characteristic. Okay? So to compute this Euler characteristic, I need to construct this simplicial complex, the order complex of that poset, with the top and the bottom removed. Okay? And so what does that look like? Well, you need to associate a new picture, the simplicial complex, where the vertices are all of these guys, all of these elements, all of these elements, all of these elements, and the faces are the chains that you see here. So, for example, you'll have a face from 2 to 2, 3 to 1, 2, 3. That'll be a triangle in your picture. Okay. And so imagine, I mean, it's tricky to draw this. I think when I did this last time, Sam asked me how I knew to draw it properly and whether it matters. And you'll see here that it's pretty hard to draw it. I have to take these 5, 10, 18 points, and I have to put them down and fill in every triangle given by any chain here. Okay? But I'm going to show you a really beautiful way to do this. I'm going to show you a very nice realization of this order complex. And the way I'm going to do that is that I'm going to perform the barycentric subdivision of the polytope. Now, let me ask you guys, have you ever seen either the word barycentric subdivision or the word barycenter? So you've seen barycentric subdivision? Has anybody seen barycentric subdivision? So where did you see that? Oh, in Polytopes, okay. Okay, so maybe if you take a course in algebraic topology, then the barycentric subdivision plays a very important role. In Polytopes, this is also a very useful thing to do. And what is barycenter? It's the barycenter of a polytope is the center of gravity, which if your polytope is a simplex, you can just think of as the point in the middle, the average of the vertices. So that's what I'm going to do here. Okay. So for every phase, I'm going to consider the barycenter. So this is easier for the edges. Okay, so for the edges, this is the barycenter of 1 and 2, the barycenter of 2 and 3, of 1 and 3. These are just the midpoints, right? Okay. And actually, these come with very natural labels, right? So I should probably call this 1, 2. I should probably call this 2, 3. I should probably call this 1, 5, etc. Maybe I'll label only the ones outside so that we can see something here. Now let's take the barycenters of the faces, of the two-dimensional faces. Okay, and so, for example, the barycenter of this face right here is, you might remember from high school geometry, where the barycenter of a triangle is. It's where the medians intersect, the centroid. Barycenter and centroid are the same thing. Okay, and so it's actually like here somewhere. Maybe this is the barycenter of 1, 2, and 3. And I'm actually going to draw what you should be tempted to draw if you remember your high school geometry. I'm going to do this. Okay. This is 1, 2, 3. And I imagine doing that for all the triangles, but I'm not going to do it because then it's going to be hopeless to see anything. Okay? But what I am going to do is that I'm going to do it for the bottom face also, because it's a little bit different. So for the bottom face, the barycenter is the center of the square. Okay? And how should I join it to the other stuff, or should I join it to the other stuff? basically what I'm going to do is that I'm going to join barycenters if one face is contained in another one. Okay, so like 3, 4 is contained in 2, 3, 4, 5, and so I join this, and you know, you basically end up with this picture like this. Okay. So what I'm doing is basically I'm telling you where, for each one of the points in this picture, I'm giving you a geometric location where you could put it. Right? I'm telling you the point 2, 3, 4, 5 that you wanted to put in your simplicial complex. Actually, you're going to put it geometrically exactly at the center of that corresponding face, at the barycenter of that face. And so that gives me a way of laying out the points. What edges did I draw? For example, I drew the edge from 2, 3 to 1, 2, 3, and the reason that I do that is that actually 2, 3 is less than 1, 2, 3 here, and so that's a chain. And so I should put that in my simplicial complex. What are the triangles in this picture? Let's look at this triangle. Where do I see that triangle here? Well, that is precisely coming from the chain from the empty set to 3 to 2, 3 to 1, 2, 3 to 1, 2, 3, 4, 5. And then I drop the top, the bottom on the top, right? Okay. So given every triangle in this picture, you can see what chain it comes from, and vice versa. So if I look at any chain from the bottom to the top in this picture, like the one from 0, from empty, to 5, to 4, 5, to 2, 3, 4, 5, to 1, 2, 3, 4, 5, you're going to find that somewhere, right? You're going to go, here's 5, here's 4, 5, here's 2, 3, 4, 5, and they form a face in this picture. Okay? And so what I'm claiming is that when you perform this barycentric subdivision, you get a simplicial complex. I mean, I hope you can see it, right? In the bottom is split into 8 triangles, and then each one of these faces is split into 6 triangles. They're all triangles. Okay? You get a bunch of triangles, and my claim is that when you do this, you get exactly the order complex that we want. Okay? And so this is precisely a realization of the order complex of P bar. Okay, so this is exactly the simplicial complex whose Euler characteristic we're trying to find. Okay. So then we get this. We get that the Mobius number of P is equal to the Euler characteristic, the reduced Euler characteristic of delta of P bar, right? But I just said that this is precisely the barycentric subdivision of the boundary of P. Barycentric subdivision of the boundary of P. Okay, this is the boundary of P. What is the Euler characteristic of the barycentric subdivision of P? Well, the beauty about Euler characteristics, which we discussed last time, is that they don't really care about the combinatorics of your simplices. They only care about the topology. And you might as well throw out all that stuff. And if you just look at the polytope itself, that's the same exact topology, right? The underlying space is the same. You're just cutting it up differently. Okay, and so the point is that this is exactly. I mean, we talked about how if you subdivide, you don't change the Euler characteristic. Okay. We also talked about how a topologist doesn't care about corners. At least, right now, if you're computing Euler characteristics, You only care about what the topological shape is, and you don't care if it's pointy or not. Topologists will look at this and will see a sphere. Okay? And so this is actually just the sphere of d minus 1 dimensions. D minus 1 dimensional sphere. With the convention that our sphere that we're used to is called a two-dimensional sphere because the surface is two-dimensional. Okay? And then if you ask any topologist what the Euler characteristic of the sphere is, they can tell you. It's almost 1, but it actually depends on the parity. And actually, I think it's minus 1 to the d minus 1, actually. Is that right? 1 minus 1. I think that's right.
Yeah, because the one sphere is 1.
So that must mean that this is not right. This is right. I think I was off by 1. Let's check in this example. Here the Euler numbers were, sorry, the Mobius numbers were 1, minus 1, 1, minus 1, 1. So the answer is 1 in a three-dimensional thing. And so it should be minus 1 to the something even. So that's right. Okay. By the way, how do you compute the Euler characteristic of a sphere? Well, you can cut a sphere however you want. Okay. So actually, what you could do is just take the sphere and think, what is the simplest? What is the easiest simplicial complex that gives you the sphere? It's just the simplex. Okay. And then you can compute the Euler characteristic very easily, and you'll see that it's equal to this. Okay. So, I mean, this is a sketch, right? Proof sketch. But it shows you how, from the topological interpretation, it's very clear what this answer should be. If you, I mean, if you're, I think maybe in a year or two this will be very, very familiar, and you'll think this is very easy. Right now, hopefully it sounds believable. Maybe that's a good look for it right now. And actually, maybe this motivates you to get excited about the day that you'll take algebraic topology. Okay. Any questions about this? Okay. So these are the, okay, that's the end of the sketch of the proof. And so let's say a little bit more about this, because we have a poset. We were able to compute the Mobius number, but maybe we want to compute the whole Mobius function, not just the individual Mobius number. Maybe you want to compute mu of f comma g for any f and g. Okay, and so that brings up the question: okay, what is an interval here? And so let me point out the next thing here. Here's a nice fact. If you look at phase lattices of polytopes, that's a family of posets. Now, when you have a family of posets, and you have been thinking about Hopf algebras for a whole semester, what should be the first question that you ask about your family of posets? Is it closed under, is it what we call a hereditary family? Is it closed under taking intervals and undertaking products? And it is. So we might call this, I don't know, for lack of a better name, let me call it LP, lattices of polytopes. So this is a hereditary family of posets, a hereditary family of intervals. So it's closed under taking intervals, and it's closed under taking products. So let's see why it's closed under taking intervals, okay? Imagine that you have some polytope here, P, okay? And you make the maybe it looks like this, I don't know. That's a polytope, and you make the lattice of faces. Okay? I want to see that every interval here can be thought of as the faces of some poset. Okay? So first, let's do something easier. Why is this the orange thing? Why is that the lattice of faces of a polytope? Let's say that this is F and this is G. Okay? So why is 0 to G a face poset? It's the face poset of whom? That's right. So every point in the phase lattice corresponds to a face here. Okay, so this G is some face here, and the orange interval is just the faces that are inside G. Therefore, they're exactly the faces of G. So this is just the face poset of G. Okay. So that's fine. That means that, remember, my goal is to prove that the green thing is a phase lattice. Okay? And so now I can now forget about this stuff and say, okay, why is this a phase lattice now? In other words, if I take an interval from some f to the top, why is that a phase poset? So let me change the picture so that we can see a little bit better what's going on here. Let's also, well, okay. I'm running out of colors here, but so the orange thing we are assuming is a face poset. So it's a face poset of some polytope. Maybe this is the polytope. Okay. And now I have F. Now, what happens if F is a vertex? Okay. Why is this blue thing a face poset? Let's look at. So a vertex here is a vertex of this polytope. Okay. So if you look at the faces of the orange polytope that contain V, I want to say that those correspond to the faces of some polytope. Okay. So the faces of the orange polytope containing V. How can I make them correspond to the faces of a polytope? What I can do is I can just chop here at V. So I just kind of make a cut at V. Okay. And then you'll see that what are the faces of the orange polytope containing V? There are this edge, this edge, this edge, this triangle, and those precisely correspond to this vertex, this vertex, this vertex, this edge, this edge. And so my claim is that this blue thing is exactly the face poset of this little polytope, which is called the vertex figure.
Where does the blue triangle have face show up?
What about the full face here of the blue triangle? Well, that corresponds to, looking out of V, it corresponds to the whole polytope. So that corresponds to the top. Okay. So if F is a vertex, This is the face poset of the vertex figure. Okay, and this is a little bit of polytope theory. Okay, and in particular, one non-trivial claim here is that if I take a slice close to V, then it doesn't really matter what angle I do it at. The combinatorics of the polytope is the same. And I hope that sounds believable to you, but it's something that one needs to prove to say this. Or rather, it's a consequence of this when we prove this. Okay. So that's true if V is a vertex. Now, if F is a vertex, then we have that, and if F is not a vertex, then you can just kind of induct. Otherwise, induct. Okay. So then, maybe F is not a vertex, but maybe in this picture is going to actually correspond to a vertex of the vertex figure, and so it'll be the face poset of the vertex figure of a vertex figure. Okay. And this is what's called the face figure of F. Okay. So the point is that you do get any interval of a lattice of polytopes, of a lattice of a polytope is also a lattice of a polytope. Okay. And by the way, this immediately says that, so a corollary of this is that if you are in this lattice of flats and you want to compute the Mobius function from F to G for any F and G, so maybe F is here, maybe G is here, what is the Mobius number from F to G? Well, you just have to look at the interval from F to G, and that's going to be this interval right here. It's this square. Okay. And you know that this square is the face poset of a polytope. Right? And being that it's the face poset of a polytope, its Mobius number must be -1 to the appropriate thing. Okay? And so what you get here is that this is equal to -1 to the dimension of G minus the dimension of F. Okay? So this is the full Mobius function of any phase lattice of a polytope. It just alternates 1, -1, 1, -1, etc. Okay? But while we're at it, intervals, we should also see that, I mean, this means that this family is closed under taking coproducts. But now let's look at products also. So if L is the face poset of a polytope P, and L prime is the face poset of a polytope P prime, then I would like to claim that the product of these two posets is the face poset of something. It's the face poset of a polytope. What do you think that polytope should be called? It should probably call the product of. It should probably be called the product. And so then you look up the literature on polytopes and see, okay, is there some notion of product of polytopes? And you'll find that there is, and that this is true. What is the product of polytopes? This is it's actually just, I mean, if you just treat this like they were sets, the definition is exactly the same. But how are you supposed to think of this geometrically? P is a polytope that lives in m dimensions. P prime is a polytope that lives in n dimensions. And so you can think of P as a vector of length m, you can think of p prime as a vector of length n. And so this p comma p prime is a vector of length m plus n, and it lives in m plus n dimensions. And so I'm making the claim here that when you do this construction, you actually get a polytope, and that polytope has this property. And these are the kinds of things that you just have to write down the definitions and make sure that everything makes sense, but it's true. Okay? Mm-hmm.
What happens to the intervals like n and
Oh, so I guess I drew this, but I didn't say it. So going back to the intervals, our goal was to show that any interval was a phase poset of some polytope. Okay? And what I said is, first of all, if this thing is the phase poset of a polytope, then this thing is the phase poset of a polytope by the first property. And now, given that the blue thing is a phase poset of a polytope, then by the second property, if you go from anywhere to the top of that guy, that's the phase poset of a polytope. And so the combination of these two is that any interval is in the family. Okay? So, okay, well, this is just yet another Hopf algebra that we haven't studied, but we have it right here. Right? Let me make sure that I can erase this, because it would be tragic if I need it again. I think it's okay. Yeah. And so, so the fact, so here's a nice proposition. I mean, it's an immediate corollary that this product makes this gives us a Hopf algebra, an incidence Hopf algebra with the usual product and coproduct. Which is not really what I was. It wasn't really my main goal here. My main goal was to prove you that these posets have nice Mobius functions. But along the way, we get this for free. So we might as well write it down. Okay? Okay. So, any questions about that before we move on? So let's discuss an application of this. An application of this Mobius function. And this is the so-called Dehn-Sommerville relations. So the question is the following. We're interested in polytopes, and we're interested in doing counting in polytopes. So in polytopes, a natural thing to count is faces, right? So, okay, I erased my square pyramid, but that's easy to draw. Let me just draw it real quick. And so you can count the faces of every dimension. Okay, and that's what's called the f vector. The f vector of a polytope P is given by f minus 1, f0, f1, up to fd minus 1, where fi is the number of I-dimensional faces. And I guess I should say that this is a d-dimensional polytope. So you count all the faces of all the various dimensions. Okay? And okay, maybe we can do this in an example. So let's do this for the octahedron. So what is the F vector here? We can call it f of p. So f of the octahedron is what? Well, first we count minus one-dimensional faces. So we know that's kind of weird, but this is just the empty set, and there's only one empty face. F0 is the number of vertices. So there are 6 vertices here. F1 is the number of edges, and there are 12 edges here. F2 is the number of two-dimensional faces, and here there's 8 triangles. And then, you see, we stop at d minus 1, so we don't count the full polytope. Okay? Yeah?
Why bother to count f minus 1 if it's always going to be 1?
A good point, and another good point is if you count this one, why don't you count this one, which is maybe more interesting. The answer, I guess the answer is that it doesn't really matter too much, but you'll see why. The answer is not going to be great, but I'm going to give you an answer. But yeah, you might as well drop it, or you might as well add it, or you might as well add this one. It's the same amount of information. Okay, so now there's another way of encoding this information, which is what is called the h-vector. The h-vector is given by h0, h1, up to hd, is given by the following equation. So if you take this, so this is something very standard that we've done a lot of times, right? You have a bunch of numbers, you have a list of numbers, we make a polynomial out of them. In this case, the polynomial is going to be, I guess, x minus 1 cubed plus 6 times x minus 1 squared plus 12 times x minus 1 plus 8. And whatever that polytope is, you call the coefficients hi x to the d minus I. Okay? So you get some numbers. So you take this polynomial I just said, x minus 1 cubed plus 6x minus 1 plus blah, 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 blah. You see what the coefficients are, and you're going to find that they are these. Okay? So first answer to Seth's question, well, actually, on the right-hand side, the numbers that appear in this equation are f minus 1 up to fd minus 1. And that's why I consider f minus 1 and why I don't consider fd. It's not a great answer, but it's an answer. Now, the other very natural question, I think, is why bother defining these weird numbers, especially because they're actually equivalent. I mean, if I tell you the f's, you can give me the h's by this formula. But also, if I tell you the h's, you can give me the f's. How do you do that? Just kind of reverse this equation. One thing you could do is say, plug in x plus 1. And then you would get that the sum of hi x plus 1 to the d minus I is some polynomial whose coefficients are the fi's. Okay. So the point is that the f's and the h's are exactly the same amount of information. The f's are much more natural, but I want to show to you that the h's are worth defining. Okay? But actually, before I do that, let me show you a nice trick. Well, no, actually, before we talk more about this, I should motivate why these numbers are worth studying, or else you shouldn't care and you should stop paying attention. Right? So why should you care about these numbers h? The reason is the following. The reason is that it's not a coincidence that this vector is palindromic. And that's something that you should be pretty amazed about, okay? Because I took some polytope, I took the faces, I got some vectors, and then I made this polynomial, and a priori ahead of time there's no reason to believe that this should be a palindromic polynomial, but it is a palindromic polynomial. Okay? And that's why you should care about it, because you would never see that in the f's right away. But when you compute the f's in this way, you're going to find that there's this beautiful symmetry. That's why you should care about it. So let me write that, but let me also write a condition that you need for this to hold. Because this doesn't always hold. This holds if your polytope is what is called simplicial. P is simplicial if all its faces, let me say if all its facets are simplices, and therefore all faces are simplices, and hence all faces are simplices. Okay. So here's an example of a simplicial polytope, because all its faces are triangles. There's no squares, or there's no pentagons, or anything like that. And actually, that's why I computed this for this polytope and not for the one that I had over there, because the polytope over there is not simplicial. And if you try to impress somebody with this trick, you shouldn't do it with that polytope, because it's not going to work. For that polytope, h is not going to be palindromic. I don't think it's an if and only if, but I don't have an example offhand. But I don't think it's an if and only if. But that's the theorem. These are the Dehn-Sommerville relations. The theorem is that if a polytope is simplicial, then the h vector is palindromic. Meaning that hi is equal to hd minus I for all I. Okay? And that shows a kind of an unexpected order inside the f vector. No, so that the question is, Lisa's question is, okay, I recognize this. This is just the third row of Pascal's triangle. Does it always happen? And the answer is no. But you might think about what polytope you can put here so that you get the nth row of Pascal's triangle. That's a nice. There you go. That's a nice question for the forum. Can you think of a polytope to feed this into, so that the h vector is Pascal's triangle, the nth row of Pascal's triangle? It can be done. So which polytope is that? Yeah. I mean, it's not obvious that it can be done, but I know that polytope. So you should try to find it.
But it does look to me from the structure of the h's that this is always going to begin and end with the h's are always going to begin and end with number 1, right?
It's very.
The highest order term is just from taking x minus 1. The coefficient on the highest order term is just going to be f minus 1. So it's 1, right?
So I agree that it's true that this number and this number are always 1. For one of them, it's very easy, and for another one, it's non-trivial. So one of these ones you can explain very easily by saying plug in x equals 1 here. Sorry, plug in x equals... Just look at the highest order term, and you'll see that you just get 1 equals 1. Okay. The other one at the other end is non-trivial, and it says plug in x equals 0. When you plug in x equals 0, you get the independent term of a polynomial. And what do you get here? You get exactly the Euler characteristic. And the Euler characteristic of a polytope is minus 1 to the d minus 1. So the reason that the other guys are 1 is because of Euler characteristic considerations. So that's kind of interesting. One is totally trivial, the other one is exactly Euler characteristic. And by the way, that shows that the Euler characteristic being equal to 1 is the special case that these numbers are equal to each other. And so you can think of the Dehn-Sommerville relations as a generalization that say not only are these two numbers equal to each other, but actually the whole vector is palindromic. Yeah?
So one of them is going to be 1 regardless of dimension, right?
Yeah.
And so from the theorem, the other one has to be positive 1 regardless of dimension.
Yeah, so I mean there is the signs work out.
Okay. So it's not really the Euler characteristic.
It's minus 1 to the something times the Euler characteristic. Yeah. Let me speaking of Pascal's triangle. So there's a nice trick to compute these numbers that I want to show to you, and then we'll prove this. So here's what's called Stanley's trick. Maybe I won't squeeze it here. Maybe I'll do it over here. Actually, I want to prove the theorem here, so maybe let's go over to this corner, and I'm going to show you Stanley's trick for computing h-vectors. So, I mean, I told you, one way of computing the h-vector is just to plug in the f-vectors and compute this polynomial and multiply out, and that's long and annoying, but you can do it. But it turns out there's a more fun way to do this, which is the following. Take the take the f-vector, which is 1, 6, 12, 8. Okay? And let me... try to... So what I'm going to do is that I'm going to do kind of a Pascal's triangle, but backwards. So I'm going to force these numbers to be what they are. I'm going to put 1s over here. Okay? This should seem very strange what I'm doing. And then I'm going to fill the rest of this as if it were Pascal's triangle. Okay? So what number should I put here? I should put a 5 so that 1 plus 5 is equal to 6. Here I should have a 5. So that 1 plus 5 is 6. What should go here? 4. What should go here? 3. And I can't really go any further. What should go here? 5 plus 7 is 12. 4 plus 3 is 7. 7 plus 1, actually, 1 is 8. And actually, I meant to also put a 1 here, as in Pascal's triangle. I mean,
And the sum is really 1 at the bottom, 2.
sure. Okay. But the point is that if you put the f vector here, and if you put 1s along here, and if you carry this process out, then what you're going to get here is exactly the h-vector. So that's kind of a fun way to compute this h-vector. And it's also a fun combinatorics exercise to prove that this is equivalent to that formula. It is. Stanley's the tricky guy. He has really a lot of nice results. I mean, this is kind of a simple result. He's a lot trickier than this, but that's a nice trick. Okay. Before I proved the Dehn-Sommerville relations, actually, let me write them in the way that Dehn and I believe Dehn and Sommerville wrote them like this. They didn't write them in terms of the h's. I think that was done later, but don't quote me on that. But you can also write the h's in terms of f's, right? I mean, you can write what this means. You can write what this means, and the Dehn-Sommerville relations look like this. Let me write them here. So this is equivalent to saying the following thing. Fk is the sum from L equals K to D of minus 1 to the D minus L plus 1, L plus 1, choose K plus 1, FL. Okay, for all K. So what I'm claiming is that this equation is equivalent, this set of equations is equivalent to this set of equations. And hopefully this justifies to you that these are really the better set of equations for this formula. They clearly are much more revealing here than they are here. But let's prove it. Okay, so let's prove the Dehn-Sommerville relations. We're going to do it as follows. We have what happens if I compute? So I'm going to do a computation. Oh man, I really wish I hadn't erased the poset here. Okay, so you can still imagine there's a poset here. It's the poset of faces of a polytope. Okay, and I'm going to imagine that I sum all these numbers. So maybe I'll at least draw a schematic picture of the poset so that we can keep track of what we're doing. So here's the full poset, here's the empty set, and then these are all the faces. And so now I'm going to go to the kth level. Okay, so these are all or dimension k. I think that's the k plus 1 level. Okay. And I look at all those faces, and for each face, I add the number from F to P. Mobius from F to P. What do I get when I do this? So here's F. What is the Mobius number from F to P? It's just minus 1 to the P minus F, right? Minus 1 to the dimension. This is just minus 1 to the dimension of P, which is D, minus dimension of F, which is K. Each one of these numbers is the same. They're all minus 1 to the D minus K. How many numbers are there here? The number of faces of k dimensions. And so this is exactly fk. Okay? And this is going to be where my left side of the equation comes from. Okay. Now I'm going to say the following thing. I'm going to say, what is mu of f comma p? Well, actually, I remember what the recursion is for mu of f comma p. Remember, to compute this number, what you do is that you look at all the numbers below it, you add them, and you take the negative of that. Okay? And so I'm going to look at all the different numbers, all of these guys over here. And I'm going to add all of these numbers, and I'm going to add them all and put minus that. Okay? So I get sum from the dimension of f equals to k, and then I get minus the sum of all of these green guys, which I'm going to call maybe g. So g needs to be bigger than f, and it can't be the top element. Okay? And I get mu of f comma g. Okay? So I get this. Now, the thing is that actually this number is also very easy because mu of fg is also minus 1 to the dimension of g minus dimension of f. That only depends on the dimension of g. And so let me just do the following thing. Sum dimension of f equals k, sum over the different dimensions that L could have, sorry, that G could have. So I'm just separating this sum by dimension. Okay? I'm adding all the G's, but I'm just separating them by dimension. And when I do that, mu of fg is just going to be minus 1 to the dimension of g minus dimension of f. Okay?
Does it matter that we don't have the negative anymore?
Oh, and this negative, let's put it in front so that I don't forget it. It definitely does matter. You can see this plus 1. That's actually that negative. Okay. So now what should we do? Well, one good thing about this is that the Mobius function is gone. And these are all just faces. Okay. So now I just have to be. Now let's do the following thing. I'm going to reverse the order of summation. Okay, so I'm going to sum over all the L's. Then I'm going to sum over the G's that have dimension equal to L. And then I'm going to sum over the F's, which are faces of G and have dimension K. So all I did is that I just reversed the order of summation, which is not going to alter the result. And I get this. Okay? And I still want the minus, yes. Keep reminding me if I keep forgetting. Okay, why is this better? Because now we're kind of taking the other perspective where we start from G. Okay? And so let me erase this. And now the G is the important one. We're first summing over G. And then we're looking at the F's that are, right, so, we fix G at level L. Okay, so this is dimension L. And now we're summing over the faces of G at level K. So what we do is that we look at the things below G. Right? And then we need to figure out how many of them are at level K. Why is this any better or any easier? Well, because there is a hypothesis that is very important that we have not used, which is that P is simplicial, meaning that all the faces are simplices. P is not a simplex, but everything below it is a simplex. In particular, G is a simplex. Okay? So G is a simplex. There it is. This is G. It's a simplex. How many vertices does it have? Well, to make a simplex in L dimensions, you need L plus 1 vertices. just like in 2 dimensions to make a triangle, you need three vertices. Here, you need L plus 1 vertices. Okay? How are you going to make a k-dimensional face here? All you have to do is just choose some of the vertices, and they're all in convex position. They're linearly independent, so any k plus 1 vertices that you choose are going to give you a face. Okay? So if I want to choose some face, like some edge, for example, I can just choose any pair of vertices, and they're going to give me a face. Okay? So this is going to be F. It has k plus 1 vertices. And so the point is that a simplex of L plus 1 vertices, if you want to count as k-dimensional faces, the number is exactly L plus 1, choose k plus 1. We're just counting faces of a simplex, and that's much easier. Okay, so this is equal to, I didn't forget the minus sign this time, minus sum over L, sum over the G's that have dimension L. And now the point is that here I'm summing the same number, minus 1 to the L minus k, and how many times am I adding it? Well, like I said, I have a simplex of dimension L plus 1. I'm trying to count as k-dimensional faces. There's exactly L plus 1. Choose k plus 1 of them. Okay? And this is taking the right shape. Again, here we have a sum over G, but what we're summing does not depend on G. And so this is just equal to minus the sum over L. We have the same sum and over again. Okay? And how many summands do I have? Well, it's the number of faces that have L dimensions. This is exactly F sub L. Okay? And I didn't forget my minus sign, which means that I'm going to take it out of here, put it as a plus 1 here, and that's the formula. Right? I hope so. Oh, okay, so that's almost the formula, except that there I have a sign of D minus K, and here I have a sign of L minus K plus 1. And so when I cancel the sign over there, I'm going to get here D minus L plus 1, which is what I want. And so that gives me the Dehn-Sommerville relations. Okay. But you'll see it's absolutely crucial here. In this computation, it's crucial that the Mobius numbers are what we want them to be. It plays a very fundamental role in this proof that this is equal to minus 1 to the this, and this is equal to minus 1 to the minus k. And from knowing that Mobius function, we get the Dehn-Sommerville relations. Okay. So that's a nice polytope fact. Any questions about it?
So many.
Too many questions? What about one question?
So I have a question. So by Stanley's trick, if you plug in any valid palindrome on H, do you then produce an F that's going to actually be realizable as a polytope? Because not every sequence of numbers that you could plug in for F is necessarily going to correspond to the face counts on a realizable polytope. But if you do this computation with a palindrome, do you get?
So it's an excellent question. If you start with some random palindrome here, then presumably they should be integers. Should they be positive? Probably, but we don't know it, right? We haven't proved that these numbers are positive. Have we? I don't think so. I mean, they are positive, but I have not proved it. Okay. But okay, so that's an example of a criteria. You cannot put any numbers here; they have to be positive. But the question is, if you put some numbers here, then you get some f vector here. Can you find a polytope with that f vector? And that's a great question. And that question is actually what motivated this stuff, because the reason to study this is that you wanna say, okay, I want to understand polytopes. So maybe I want to understand the phase numbers of polytopes, and so the, if you, I think it's always good if you enter a new field, you should ask the most naive, hardest question and see if it's answerable. So, for example, you can say, okay, what are the possible f-vectors of polytopes? Can you, given a polytope, you get an f-vector. And now, if I give you an f-vector, is it possible to find a polytope for it? That might be an easy question. It might be an impossibly hard question. And I think by now we agree that this question is too hard. It's too hard. And actually, that is one reason that we focus on the simplicial case. Because in the simplicial case, we have a lot more structure. Okay? So in the simplicial case, we can say, okay, here we have, for example, this result that gives us more structure on what these f-vectors can look like. But it's not enough structure because, for example, what are the h's that can appear? Okay? And this is part of a very long story that actually just had a new development last week. And maybe I'll take it to the forum. But basically, the question is very interesting, what these numbers can be. Many people have made it their career on trying to answer this question. And the fact is, no, you cannot just put some random numbers and get a polytope, or get a simplicial polytope. For example, how big can these numbers be? Okay, that's one of the things that is best understood. But maybe what I'll do is that I'll put on the forum some pointers as to what the current status of that is. But the answer basically is that it's a great question and it's a very alive question that we don't really. I mean, there's 100 different questions that you could ask here, and most of them are not. No, most of the answers are not no. I think another natural question that you should wonder is, okay, well, why is simplicial? Should I care about simplicial polytopes? Is it likely that I'm simplicial, or is it unlikely that I'm simplicial? What do you guys think? If I just throw some points in space, and I say, okay, there's a polytope, I just throw some points in space, is that likely to be simplicial or not? It's extremely likely, right? That's right. I mean, you have to be extremely unlucky to get a square to be a phase, because with probability 1, 4 points in space are not on the same plane. Okay, and so actually, being simplicial is something that almost every polytope satisfies in just about any reasonable measure of almost every. And it is true that if you throw some points at random, then with probability 1, the polytope that they determine is simplicial. Okay? And so this condition, it would be nicer if we didn't have to put it. But given that we have to put it to get this result, at least I think it's kind of a moral victory to know that usually this happens. So maybe this is not such a terrible condition to put on it. Okay. Okay. Maybe the last thing that I should tell you, I'm running out of time, so I'm just going to have to say it in words. Okay? But these H numbers have a very nice interpretation. And they kind of say the following thing. They say, assume you have your polytope. Okay? It's over there somewhere. And then you kind of travel on a straight line and you go across the polytope. And then you see how many. I'm running out of time and I'm saying this in a very imprecise way, but you ask yourself, how many faces do you meet at each moment in time? Okay? And in a precise sense, first you're going to meet one face, then you're going to meet 3 faces, then you're going to meet 3 faces, then you're going to meet 1 face. Okay. Where the sum of these numbers is the number of faces. The number of facets is what I mean. I'm sorry. Here, 1 plus 3 plus 3 plus 1 is 8, because that guy has 8 facets. And there is a well-defined sense in which you can say if you pierce through the polytope, you kind of meet them first 1, then 3, then 3, then 1. This is what's called a line shelling of the polytope. And again, maybe I'll leave the more precise statement to the forum, because I think the video is about to cut off, and I don't want to be cut off explaining it. So, but yeah, the point is that those numbers also have a very natural interpretation, which shows that they're positive, because they count something. Okay. So I ended up getting carried away talking about polytopes more than I meant to, but maybe that's not a bad thing anyway. And we'll see how this is related to what we've been doing also. So, okay. We'll stop there.